The question asks us for a definition of vapor pressure and then the value of the vapor pressure for 2,2 dimethyl propane. We also have to give a reason for how we deduced the vapor pressure of this compound. We are given a table with 5 compound names, their molar masses, and the vapor pressure of 2 of the compounds. The missing vapor pressure values we have called X, Y, and Z, and these values are 58, 146, and 79 kilopascals. But we don't yet know which value belongs to X, which to Y, and which to Z. When a liquid is put in a closed system where particles cannot escape, some of the liquid particles evaporate, and some condense to reform the liquid. Over time, if the temperature is held constant, an equilibrium forms where the rate of evaporation is equal to the rate of condensation. The pressure of the gas or vapor in this equilibrium system is called the vapor pressure. So we can define vapor pressure as the pressure exerted by a gas which is at equilibrium with its liquid in a closed system at a fixed temperature. The vapor pressure of a substance at a certain temperature is dependent on how volatile it is, that is, how easily it evaporates. And its volatility depends on the strength of the intermolecular forces of attraction. So to find the vapor pressure of 2,2 dimethyl propane from the 3 given values, we must start by understanding and comparing the structures of compounds X, Y, and Z, so that we can then deduce the strength of their intermolecular forces. Pentane is a linear 5-carbon chain. Because pentane molecules are linear, they can get close together and have a high surface area in contact with each other, or we could say they have high surface interaction. This results in relatively strong van der Waals forces of attraction due to temporary dipoles. A relatively high amount of energy is required to overcome these forces to evaporate the liquid molecules, and therefore the vapor pressure which results is low. 2-methylbutane is slightly branched, resulting in less surface area interaction between molecules, as they can't get close to each other along their lengths. So the van der Waals forces are weaker than in pentane, and less energy is required to overcome these forces, making this compound more volatile than pentane. A higher volatility results in a higher vapor pressure. Then 2,2 dimethyl propane, which has the same molar mass as compounds X and Y, has even more branching and even less surface area interaction, as the molecule is very bulky. And so the van der Waals forces are even weaker than the previous 2 compounds. Even less energy is required to overcome these forces to evaporate these molecules, and so they are the most volatile compounds of X, Y, and Z, and produce an even higher vapor pressure than compounds X and Y. From this, we can assign the vapor pressures given. 58 kilopascals, the lowest value, belongs to pentane, 79 to 2-methylbutane, and the highest vapor pressure value, 146 kilopascals, belongs to 2,2 dimethyl propane. Finally, we will need to explain this deduction using the reasoning we have discussed.